Okay, guys, so it was brought to my attention that the previous video that I uploaded went dark for the last 9 minutes of it, and I apologize. I had no idea. So I want to pick up where I left off there and go over the one of the examples for the lecture on 7.2. So here we're learning about random variables, and recall that we use a big capital X quite often, or a big capital letter in general, to represent what we're calling a random variable. Random variables behave differently than normal variables insofar as we do not know precisely what the output will be for a given input, but we can assess probabilistically what the likely outcome will be for a certain input. So random variables are dealt with, their outputs are dealt with using probability as opposed to certainty. Okay, so in this example, we're defining the random variable X to be the sum of the two upper faces when rolling two dice, or a pair of dice. So we're rolling the dice. Each die has 6 faces, each face with a number on it from 1 to 6. And we're taking those two results when we roll the two dice and adding them up, okay? So this random variable defines a number of events and a big sample space, right? So the sample space S, which I've sort of messed up here, and I'll explain this picture better in a second, but try to ignore the diagonals that I've circled. The sample space S consists of pairs of results, one result being for the first die, the second result being for the second die. So this particular coordinate pair, 1, 1, represents the event when you roll the two dice and you get a 1 and a 1. Okay, and so on and so forth. So here we've rolled a 1 and a 2, a 1 and a 3, a 1 and a 4, so on and so forth. And you can see that I've listed all of the possibilities, the complete sample space here. So we fix the first coordinate at 1, and then let the second coordinate range from 1 to 6, and then we stop. And then we fix the first coordinate at 2 and let the second coordinate range from 1 to 6 and stop. And we continue this pattern all the way till the end. And so we can see that since there are 6 possibilities for the first slot and 6 possibilities for the second slot, that there's a total of 6 times 6 possibilities, or 36 possibilities in our sample space. Okay, so using this random variable, we can write down the probability distribution. So here in this table, we are representing all the possibilities for the random variable. The random variable X equaling little x, where the little x represents the actual output, and the big X is just the random variable. So this is the name for the random variable, and the lowercase x is one of the possible outputs. If we look at all the possibilities, we can either roll a 2, a 3, a 4, a 5, a 6, a 7, 8, 9, 10, 11, or 12, where these numbers are coming from adding up the two results. Okay, so this is all the possibilities. In the next column, we have the corresponding probabilities, right? So let's just unpack this a little bit. If I look at the possibility of rolling a 2, how many ways are there to roll a 2? Well, there's only one way to roll a 2, and that's precisely when you roll a 1 and a 1, because 1 plus 1 equals 2. There are no other ways to roll a 2. So the probability of rolling a 2 is 1 out of 36, where the 36 is coming from the total size of our sample space. So out of the 36 options, there's only one option that gives us a 2. Okay. If we move on to a 3, we want to use the we want to determine the probability of rolling a 3. Well, this is a little bit more complicated, and in fact, this is why I've circled these diagonals, because if I circle the diagonals, you can actually see all the ways of rolling different numbers. So the first diagonal here, I have the event of rolling a 1, then a 2, or a 2, then a 1. And both of these add up to 3. So there are 2 ways of rolling a 3. So 2 out of 36 ways of rolling a 3, which reduces to 1 out of 18. We can keep doing this. If we look at the outcome of rolling a 4, that actually is captured on the next diagonal. And so here we can roll a 1 and a 3, a 2 and a 2, or a 3 and a 1. All of those add up to 4. So that's 1, 2, 3 ways of rolling a 4. So down here, the probability of rolling a 4 is 3 out of 36, which reduces to 1/12. And so we can play this game with all of the possible sums. And each time we're just moving down a diagonal, right? So if we look at rolling a 5, we've got 1, 2, 3, 4 ways of rolling a 5. So 4 out of 36, which reduces to 1/9. Look at the ways of rolling a 6. We've got 1, 2, 3, 4, 5 ways of rolling a 6. So that's 5 out of 36, which doesn't reduce any further. Then finally, when we reach 7, we have the most possibilities for 7, because we can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. And that's 1, 2, 3, 4, 5, 6 ways of rolling a 7. So that's 6 out of 36, which reduces to 1/6. Now, what you'll see moving forward as we look at 8, 9, 10, 11, 12, is that the ways of rolling these higher numbers start reducing. And we can see that kind of geometrically with the size of these diagonals. They start getting smaller and smaller. So the ways of rolling an 8 are 1, 2, 3, 4, 5. 5 out of 36. The ways of rolling a 9 are 1, 2, 3, 4. 4 out of 36, which is 1/9. And we continue this pattern all the way down to how many ways are there to roll a 12? There's only one way to roll a 12. So that's 1 out of 36. So one thing to pay attention to here is that if we look at the distribution of probabilities, we see symmetry. It starts at 136, then goes 1/8. Sorry about that, y'all. So it starts at 136 and then starts moving up until it gets to 1/6. And then it starts counting back down. And notice that the probabilities are exactly the same on the other end of the possibilities. So we call this a symmetric distribution. And if we plot the histogram for our random variable, we see the symmetry in the histogram. It has this, it's this nice sort of bell curve looking shape. And the bars here represent the probabilities, the red bars. And we can see that the shape here has symmetry, that if I cut it along this center line, it's the same to the right as it is to the left. So we call that a symmetric probability distribution. Okay. So this is how we can use random variables to mathematically model the outcomes of certain experiments without actually having to conduct the experiments and determine the probabilities empirically. Okay. So I will be posting some more videos going forward. I had someone request that I post some more examples. So I'm going to do some practice problem sessions that I will upload in addition to the proper lectures that will hopefully help all of you going forward. I'm also going to enable the view an example and help me solve this feature on the homeworks, just to help you guys get over some of the obstacles of translating the theory, which I go over in the lectures, into applications. So I do want to be clear about this, that in a college setting, professors generally go over the big theory. They show you how the system works, and then you're expected to figure out how to apply the theory. And if you have a trouble with the problems in the homework, it's not because I haven't gone over enough examples, although I can try to go over more, but it's that you need to try to seek out help otherwise. There's sort of an ecosystem in college where professors give you the general theory, and then you work with your peers, your classmates, and most importantly, with tutors to help you work through the problem sets and understand how to apply the theory. So if you're having a lot of trouble, I really highly recommend that you seek out tutoring, either private or through the tutoring services that are offered through the university, which are free of charge. Okay. I will try to post more a video of me working out some specific problems, but that certainly won't help you solve every possible problem that you're going to see in the homework. And I highly recommend that you work through it yourself and then take the toughest problems to a tutor and have them show you how it works. Okay. So that concludes section 7.2, and I'll be posting some more videos shortly.